Hey guys, welcome to another video on our Chapter 7 unit. This time we're looking at radioactivity. Radioactivity is an atom that emits a particle due to its instability and it's trying to become more stable. So this is, in some ways, you can imagine back when we looked at 7.1 and we were looking at excited states and things like that. So when we're talking about where were those energy diagrams? Yeah, okay. So here we're looking at um, an atom being at excited states and also at a ground state, which is a more stable state, okay? To the point of ionization where it's losing an electron. So there's various states of excitement for an atom. And what we're actually trying to look at is that some of the atoms are actually unstable and they're trying to do something to themselves to become more stable. So radioactivity is about this process of an atom trying to make itself more stable. Um, so in terms of particles that it emits, we're looking at what we call radioisotopes. And these are alpha particles. These are Greek letters here. So that's the alpha particle, beta, and gamma, which is actually our photon. Okay, and so we'll be learning about these three guys in this video later on. And so first off, with regards to this graph, this is definitely a graph that you guys must know, and it's almost guaranteed that you will get some form of question on this. And what it's highlighting is that first off, the solid line in the middle, the dark line in the middle, is where the number of protons equals to the number of neutrons. So when you guys are looking at something like the periodic table of elements, generally speaking, for the first 20 elements or so, it's actually pretty balanced. The number of protons and neutrons are roughly about the same. And then as you get to heavier elements, then the number of neutrons starts to increase. And there's a few different reasons for that. But what you see here in the purple line is that as elements get heavier, as more protons get pushed in together, there are more neutrons. So it's actually a little bit off. It gets a little bit higher above the 1-to-1 ratio, where there's exactly equal number of protons and neutrons. It starts to go up more and more, and we see more and more neutrons are needed to keep the object stable. And so the part in yellow is the unstable atoms or elements. So if you have too little neutrons or if too many neutrons, it can also make the atom itself unstable. Okay. So we're going to look at alpha and beta decay in this video, and then we'll cover gamma and radioactivity or half-life in the follow-up video after this. Okay. So alpha decay, we're looking at a mother nuclide. So first off, we have the original or the mother nuclide. And then what happens is that the daughter nuclide, it will then turn into a different element actually, because it's going to lose 2 protons and it loses 4 nucleons overall. And what happens is that it's emitting what's called an alpha particle. Okay, so the alpha particle is actually a helium nucleus. Okay, so the differences between our alpha particle and our helium atom is a helium atom is a balanced atom, meaning it has no charge. Okay, so there are 2 protons and there are 2 electrons as well. So that makes it perfectly balanced at no charge. Okay, however, an alpha particle doesn't have the 2 electrons, and so it is just purely the nucleus, meaning it has a +2 charge. And actually, it actually does pick up loose electrons from other elements very quickly, but we don't really talk too much about that. But if you're curious, when this nucleus of a helium um, element flies out from the original mother nuclide, it will eventually pick up some more electrons. Okay, so that's what we call an alpha particle. So sometimes you might see, usually we write it as the alpha particle 4 and 2. Okay, so here we have an example of uranium decaying into, I think that's thorium, or yeah, I'll have to check that one up, TH. And so an alpha particle is a resultant of that. This is the after situation, whereas this one here is before situation, before. Okay, and a few other interesting pieces of connection for you guys is due to the conservation of momentum. So you can imagine a uranium particle is much, much heavier than an alpha particle or the nucleus of a helium element. And so the uranium is moving very slowly this way, whereas the alpha particle is moving extremely fast in the other direction because there's just so much more mass here compared to a tiny little bit of mass there. And so an alpha particle actually reaches at about 5% the speed of light, and it has about roughly, most alpha particles, it does have a range of, I think it was about 4 to 8 mega electron volts, but most tend to be around 5 mega electron volts. Okay. All right. Next up, we have beta decay. So beta decay is doesn't emit particles that are as big. It emits what is called it emits an electron as well as what is called an electron neutrino. So V is actually the Greek letter. I think it's nu. So nu, nu, and so that's where the idea of the neutrino. They're using the Greek letter nu to represent neutrino. That's the V. Oh, sorry, I got it really nicely down there. Okay, so the bar is an anti-particle. Okay, so V is nu for neutrino, and then E is the symbol for the electron. Okay, so that's how we get that's the symbol for the electron anti-neutrino. And the electron antineutrino actually has no charge, as we can see down here. Okay, so usually we focus on the electron, which is our beta particle. Whoops, shouldn't have erased that. So usually we focus on the electron, which is our beta particle, but do be aware that there is also an antineutrino, electron antineutrino with that as well. And actually what also happens is that the element itself also changes because it's losing a negative charge, it actually gains a positive charge. And we'll see this a little bit later in our questions down here. So actually, let's look at the beta decay because we were just talking about that. So a carbon 14 actually turns into a nitrogen. So nitrogen, you might remember, is 14.7. Okay, whereas carbon is 12 and 6, if you look that up on the periodic table of elements. So this is from the periodic table. So in terms of this question, write down the beta minus decay of C14 into nitrogen. So we have 14, 6C. So that's before, and then afterwards it turns into, it's not losing any of the nucleons. Okay. And so it becomes nitrogen, but it also has the beta particle, which is -1, but it doesn't have any neutrons. But there's also the electron antineutrino as well, 0 and 0. Okay, so that's the answer to that. And the other one, this one is quite straightforward as well. Write down the nuclear reaction for alpha decay of radium. So radium is the starting element, Ra, 22688, and this is decaying into radon. And then we know there's an alpha particle, which is going to be 4 and 2. So the difference of 226 and 4 is going to be what goes there. So 226 minus 4 is 222 nucleons. And then 88 minus 2 is going to be the number of protons in radon. Okay, so pretty straightforward, I hope. And we'll be back with the follow-up video on gamma radiation and half-life. Okay, thank you guys for watching.